Machine learning has become simplified. Similar to how Ruby on Rails made web development approachable, scikit-learn takes away much of the frustrating aspects of machine learning and lets the developer focus on building functionality with high-level APIs. Harald Borgen is a developer at Xeneta. He started programming fairly recently, but he's already built a machine learning application that cuts down the time that his sales team has to spend qualifying leads. What I found most interesting about this episode was that machine learning gets used by a single developer to solve a simple business problem and deliver solid value. This is in contrast to how many of us think about machine learning as an intimidating tool that requires a large team to do anything meaningful. Before we get to this episode, a few quick announcements. If you're interested in advertising on Software Engineering Daily, send me an email, jeff@softwareengineeringdaily.com. There are more than 14,000 engineers that listen to Software Engineering Daily on a regular basis, so it's a great place to get your product out into the ears of developers or to advertise available jobs that you might have at your company. Also, if you're an engineer that's looking for an open source project to work on, check out Software Daily at softwaredaily.com. This is an open source news and information site about software. It's being led by Jeff Tribble, a member of the Software Engineering Daily community. You can also check out softwareengineeringdaily.com, which is the website for this podcast. You can find links to the Slack channel, my Twitter account, my email. You can find a link to sign up for our newsletter, Software Weekly. And with that, let's get to today's episode. Continuous integration allows teams to ship software faster. SnapCI is a continuous integration tool built by Thoughtworks, and you can go to snap.ci/softwareengineeringdaily to find out more. Snap knows all about your Git branches and integrates seamlessly with GitHub. Snap can run your tests in parallel for fast feedback, and Snap allows you to model your build as a sequence of stages, from the fastest tests to the more comprehensive ones. Configure some of your stages to be automatic and some to be manual, in case you want to have more control over your deployment. SnapCI embodies the lessons that Thoughtworks has learned from 20 years of software delivery, the same lessons that have been written about by Martin Fowler and Jez Humble. Check it out at snap.ci/softwareengineeringdaily. Again, to check out snap.ci and support Software Engineering Daily, check it out at snap.ci/softwareengineeringdaily. Harald Borgen is a developer at Xeneta. Per, welcome to Software Engineering Daily.
Thanks, Jeff. It's a pleasure to be here.
Absolutely. So let's start by talking about your company, and then we will get into the machine learning for sales post that you wrote on Medium. What does Xeneta do?
So at Xeneta, we work to create more transparency in the sea freight industry. So what that means is that we help shippers, that could be chemicals companies, automotive companies, or whatever companies that use sea freight or has sea freight somewhere in their supply chain. And we help them save money on their sea freight, basically, and spend their sea freight budgets more efficiently.
So explain why there are a variety of different ocean freight rates. Why is this not an efficient enough market that the rates are somewhat standardized?
So the thing is, there are tons of companies offering sea freight services. There are shipping lines and there are a bunch of freight forwarders. I think there are around 10,000 different freight forwarders around the world, which basically offer to get your stuff from China to, for example, Netherlands in a container. This market has been lacking transparency all the way since it started. So the thing is, it's a big, chaotic industry which is based around Excel sheets. So just having an overview over the various prices out there is a really difficult task.
So give me an idea of how you find a customer who you might offer your freight intelligence service to.
So we find our customers now by doing outbound sales, basically crawling through the internet, looking for companies which we think might have sea freight as a part of their supply chain. And we reach out to them and basically tell them about our product. And the way our unique selling proposition is that we have more data about this market than anybody else. Because what we do, we basically crowdsource the rates. So our customers get access to more rates than they can ever investigate themselves. And it grows as our customer base grows.
So is the sales process, it sounds like since you're dealing with companies that are shipping large amounts of freight, it sounds like these are typically large companies. Is it a long lead time? Does it take a long time to close a sale?
Yeah, it takes everything from a few weeks to many months.
Okay, so because it takes so long to make an individual sale, I imagine that it's quite important to select the right businesses that you actually engage with and start the process of discussing, hey, you should use Xeneta because you should be finding better ocean freight rates to ship your tons of chemicals or whatever, pianos you're shipping across the ocean.
Yeah, every lead that turns out to be a disqualified lead is a waste of time for the sales team. And a lot of time goes into looking for companies and then trying to qualify them. Looking at how much revenue they have, how many employees they have, what kind of products they sell, and how they're structured to figure out if they actually ship containers themselves or buy containers, sea freight themselves, or maybe basically outsourcing it. Or it's a lot of different things you got to take into account to reach the conclusion that these are someone we want to contact and try to sell to.
And you have a business development rep who works at Xeneta, and his name is Edvard, and one of his jobs is to track the sales leads. He looks at the sales leads, he looks at the set of companies in a spreadsheet, and his job is to pre-qualify those leads and say, are these companies worth reaching out to? Could you give me an overview of his job? What does his job of qualifying sales leads, pre-qualifying, what does that job entail?
So, first of all, he's not the only one. We have around, I think it's 12 sales reps now who do this every day, basically. So I'm not a sales rep, so I can only speak on behalf of what I see myself and the impression I get of how they work. But basically, it all starts with finding leads, and you can do that in a ton of different ways. You can search for categories and search on listings. Some countries have open listings over, for example, companies which import goods through sea freight. For example, the US. Some companies doesn't have that, but they have, of course, listings over their public companies. So you just start somewhere and looking for companies which you assume has got something to do with sea freight. And of course, we have people from other industries and from the sea freight industry who generally know a lot of companies and have domain knowledge into industries. So they perhaps have a certain idea over which companies they can reach out to.
So given that there is this large scale of different companies that you have to sift through to figure out who is a good potential customer, and given the fact that you have a large amount of sales reps, and it sounds like the force is potentially growing, it would make sense to build some software that supports this task of pre-qualifying sales leads and figuring out who are the companies that are worth reaching out to. So, as a developer, you wanted to build a machine learning algorithm that would improve the process of sifting through these potential customers. What was your hypothesis around the machine learning algorithm that you were building?
So when you're looking for these companies, these potential customers, one of the most important activities is to simply go to their website and read about them. And if you have a list of leads and you go to their websites and you read about them, you often get a notion on whether or not they're a potential lead for Xeneta. So basically by reading, we are a consulting firm that specializes on taxes and blah, blah, blah. If you read that, you very quickly realize, okay, this company has nothing to do with sea freight. But if the company says we are the Europe's biggest producer of wooden chairs, then you kind of, okay, this might be a company that does sea freight. Because if you get my point, you draw some conclusions based upon just a short description.
So you're talking here about the company description.
Yeah.
And this is basically, you find the elevator pitch of a company somewhere on the website. Is there a place where a company typically lists its company description?
That's hard, but you can normally find descriptions on their website, of course, and on their about pages, also on their social media profiles. So our theory then, or our hypothesis, was that it shouldn't be that difficult for a machine learning algorithm, given that we structure this data properly. It shouldn't be that difficult for a machine learning algorithm to roughly guess whether or not the given company is involved in sea freight or is potentially involved in sea freight.
Did you gather these company descriptions manually?
Yeah, so when building this algorithm, we needed a big testing data set, and the data set needed to consist of both companies that are qualified and both companies that are disqualified. So finding the qualified companies was pretty easy because we could just pull out 1,000 companies from our database. I mean, companies that we either have sold to or have been interested in, or, I mean, we've been involved with a lot of companies throughout the last 4 years, and we could just basically use that list because they're all qualified companies. And on the other hand, we had to find a list of disqualified companies. That's where we started getting into troubles because that's not as easy. So Edward basically had to get a bunch of lists of companies from various sources and then manually disqualify 1,000 companies.
So for people who are not familiar with machine learning, explain why you need a set of both things that are qualified companies and a list of things that are disqualified companies.
Yeah, so the way any machine learning algorithm learns is by looking at data and examples and adjusting their parameters slightly at every iteration. So that's why you have to so-called train these algorithms. You feed them a bunch of data and they look at every single company and looks, okay, this description is a qualified company and it contains the words shipping and chemicals and whatever, but shipping related words. And then it looks at another description which contains, for example, business intelligence and lawyers and words that are not related to sea freight at all. And then as you feed this algorithm more and more data, it slowly starts to recognize on its own what is a qualified company and what is most likely not a qualified company.
So you have these 2,000 companies, you have gotten their descriptions somehow. So for each company, you have a description. 1,000 of those companies are qualified. So you have descriptions that are associated with companies that are good leads for your sales reps. And then 1,000 companies that have descriptions that are associated with disqualified companies. So you have 1,000 companies that are business intelligence or law companies that have nothing to ship overseas.
Yeah.
So once you have these 1,000 qualified leads and 1,000 unqualified leads, these are going to serve as your training data, as you said.
Yeah.
Before you can use them for training data, you first need to clean this data. Describe what the data cleaning process is for those who don't know.
So the data cleaning is, together with the data gathering, very often the most time-consuming part of doing machine learning. Because the algorithms, they understand numbers, or they work with numbers. So you somehow need to transform all of this raw text into numbers, basically vectors. In our algorithm, one description is a 5,000 items long vector, each of the items being a number, basically. So what you then have to do is, first of all, you do various natural language processing techniques, which is, for example, you remove stop words, which is words that contain very little meaning. For example, it, as, and. I mean, these are words that humans use when we talk to each other, but in order to understand whether or not the description describes a company that does sea freight or not, they don't give a lot of meaning. So that's one thing. And another thing is, for example, stemming the words. That is basically to reduce each word to its stem. So, for example, container and containers would be stemmed to contain or contain. Yeah, I mean, every single...
It's like the removal of suffixes or prefixes that don't really add anything to the word. Like even something like, if you had a sentence that had the word leader and the word provider in it, you might want to remove the ER at the end of leader and the ER at the end of provider.
Yeah, because leadership leaders and
or providing, leading, these words can all be reduced to their stem. Leader and leading can both be reduced to the word lead, which can add a measure of consistency to the different sentences that are involved in these descriptions. And again, just for people who are a little confused right now, we're talking about cleaning the descriptions of these companies. You've gone to the website, you've gotten the description of this company, you have classified that description as being either qualified or unqualified, and now you're cleaning that data so that it is, whether it's a qualified description or an unqualified description, it is being cleaned so that it is standardized.
Exactly.
Okay. So once you have cleaned the data, you get these descriptions that don't even look like readable sentences. You get these jumbles of words that are stemmed, they've been cleaned. The words don't even look like human readable words. But you've got this reduced vocabulary of words. Why are these types of sentences useful? Since you've reduced these descriptions to things that are not even readable by a human, why are these useful?
So they're not useful yet. We're not finished with the cleaning. Because the next step now is to turn this into something that the machine understands, which is basically numbers, or something that the algorithms understand, which is numbers. But now that we have a much lower vocabulary than we would if we just took the raw text, we can easily create vectors from each of these descriptions. And here we use something which is called the bag of words. And the bag of words basically says that it's a vector that describes which words that appear in the given description. So this might be a bit too complex or it's not very complex, but it's a bit hard to describe here in this podcast. But what you
I think the bag of words, it transforms a sentence into a frequency count of words within that sentence.
Exactly. That's exactly what it is. Very good explanation.
So bag of words turns these descriptions into vectors. So at this point, to give an overview of the process, you've taken the company descriptions, you have removed stop words, and you've stemmed these words so that they look like just strange, non-readable sentences, and then you have turned these sentences into frequency counts, basically a mapping of each word to the frequency that word appears in that given company description. So now you have 2,000 mappings of words to frequencies of those words. Yeah. What can you do with the vectors once you have created that bagging of words?
So now you have something to work with. And this is where the machine learning starts, because a vector, an input vector, that's basically a feature vector. So, and when you when you do machine learning, you feed the algorithm with data. And that data is is represented as features. So if you're, for example, training an algorithm to guess house prices in an area, the features would be, for example, how many bedrooms the apartment has and how many square meter it is, how good the school ratings are in this area, and so forth. And now we have vectors with features where every feature represents a word. So it's these, as you said, frequency counters. And they're 5,000 items long, which, because 5,000 is the size of our vocabulary, and contain mostly zeros, but some numbers here and there, representing the frequency of the word.
Right. They're 5,000 long because they're normalized.
Yeah. So they have to be in the same size. So that's what this bag of words technique does. So it kind of translates descriptions of any given length into vectors of length 5,000, which then is something you can feed into any machine learning algorithm, or at least most of them. And they will, in various degree, be able to then predict whether or not the vector represents a description of a company that should be qualified for Xeneta, or represents a description of a company that shouldn't be qualified for Xeneta.
Right. And before you feed it into the machine learning algorithm, you might want to run a Tf-Idf transformation on the vector. That's term frequency, inverted document frequency.
Yeah.
We don't have to discuss exactly what Tf-Idf is, but maybe you could explain why it's useful to run on these vectors.
So it's short for term frequency, inverse document frequency. And the idea is that if a word, it kind of weighs the words, or the importance of the words based upon how often they appear in the total corpus, in your total corpus of words, versus how often they appear in one description, the one you're looking at the moment. And if a word appears 5 times in a description, but it also appears 5 times in all the other descriptions, then it's most likely not as important as if it appears 5 times in one description and almost never in the other descriptions. If you get my point, you kind of,
yes.
So a word like the, for example, would appear in probably all the descriptions, but they're not important. I mean, if you look at one description, it might look like an important word because it appears 5 times, but they're in all other descriptions, meaning that it's probably not an important word after all. However, we've already removed the word from the stop words, but that was just an example.
Sure, absolutely. Podcasting full-time is a great career, but if I ever return to the normal world of work, Hired.com is where I will start my job hunt. Hired.com removes the frustration of searching for a job. You just fill out your profile and the jobs come to you. Facebook, Uber, and Stripe are a few of the companies that are hunting for engineers on Hired. Go to hired.com/SE daily to try it out and get an extra $1,000 signing bonus just for using the URL for Software Engineering Daily listeners, which is hired.com/SE daily. So if you want to try it out, go to hired.com/SE daily. The demand for engineers is higher than the supply. And on hired.com, that translates to higher salaries and happier careers for the engineers who find a job on Hired. I used Hired to find a job before I became a full-time podcaster. And the experience was so good because Hired connected me with a talent advocate who worked with me to find a job that was a good fit. And the talent advocate answered my questions about negotiating salary and finding remote work, which was something that was really important to me at the time. So check out hired.com/SE daily and get a $1,000 signing bonus upon finding a job, which will be a great job that will give you the respect and the salary that you deserve as a great engineer. So check out hired.com/SE daily. It would support the show. And now let's get on with today's episode of Software Engineering Daily. So now we have cleaned and vectorized and transformed our data. We're ready to put it through an actual algorithm. And in order to do that, we need to slice the data into 70% training data and 30% testing data. We're going to put 700 of each of the 1,000 companies in each set into training data, and the other 300 companies in each set will be testing data. Explain the reasoning for why we are splitting the data up here. Why are we making training data sets and testing data sets out of our 2,000 companies?
Yeah, so that's critical when you do machine learning. You should never, ever test and train on the same data set. You should split it up in two sets. Because if you test and train, if you train your algorithm on the entire corpus of data and then you test it on the same data, what the algorithm then does is, because it measures its success by how correct it is at classifying, then it becomes really good at classifying exactly those 2,000 examples. And it ends up overfitting to the data. However, what you wanted to do is you wanted to be very good at classifying like general company descriptions. So you give it a little bit of your, or you give it a chunk of your data, for example, 70%, and you train it on that data. And then you go to the remaining 30% and test it on those examples, which aren't exactly similar to your training data, but hopefully share some similarities, but there are differences there. So the algorithm will then measure itself by how well it manages to classify data it hasn't yet seen, if that makes sense.
Right. No, absolutely. And then in order to actually train an algorithm, we're going to test two different algorithms. So you tested both random forest and k-nearest neighbors as machine learning algorithms to try to find a machine learning algorithm that would give you good details, good results. What do random forest and k-nearest neighbor algorithms do? I mean, you don't have to explain these in detail, but maybe you could give an overview for how they work and why you were testing two different machine learning algorithms.
Yeah. So I used k-nearest neighbor and random forest because they seemed most promising as I started out to test various algorithms. And I actually tested a few others, but they didn't give good enough results to continue pursuing. And random forest is just a forest of decision trees. Just basically a bunch of if and else's, which splits the data into various parts and then classifies based upon that. And k-nearest neighbor is an algorithm that looks at descriptions, and looks at its neighbors. So you take one description, which, for example, is a qualified Xeneta company, and you look at that vector, and you look at the vectors that resemble that vector the most, and you say, okay, these 5 vectors resemble this vector fairly well, and this vector was a qualified company, so we'll guess that the vectors that resemble this one, the nearest ones in the vector space, also are qualified companies. That's a very rough overview explanation of how at least I understand these algorithms.
Sure,
yeah. That being said, I'm not an expert at the algorithms in themselves. I'm using the scikit-learn library of Python, which basically give you these algorithms out of the box.
Right, and I think this is actually a very practical point that maybe you don't really need to know in super intense detail how these algorithms work. You just need to know when to use them and how to test them against each other. So in your case, k-nearest neighbor performance was much better than random forest. Explain.
No, the other way around.
It was the other way around. Random forest was better. Okay, so random forest performed better. Explain how you measured these two algorithms, how you measured their performance against each other.
So you can measure them in various different ways. The easiest way to measure is basically seeing out of our testing data, how many correct classifications does the random forest manage to do, and how many correct classifications does the k-nearest neighbor manage to do. Basically saying how many rights did you have of the 600 companies we tested you on? How many times did you guess correctly? And if you can go a bit deeper as well, and how many false positives did you guess, or how many false negatives did you guess? And those may be of various importance. For example, for us, it's important that it's okay if they classify someone as an interesting company, even though they're not. However, it's a worse mistake to classify a company as not interesting if it's actually interesting.
Right.
So you can do that in different ways.
So essentially what you did with each of these algorithms is you take 700 companies that are classified, 1,400 companies that are classified. You take 700 companies that are qualified leads, and you put it through each algorithm, and you say, okay, these are qualified leads, and then you take the other 700 that are unqualified, you put them through the algorithm as labeled as unqualified leads, and that's how you train the algorithms. And then you put the other 300 of each type of company through as testing data to see how, that's how you're measuring the performance, is you're using that testing data, the labeled testing data.
And when we're testing, we're not telling them, of course, how they're labeled, each of the different examples, descriptions. We're just giving them the descriptions, and then the algorithm guesses, oh, I think this is a potential customer, this is not a potential customer, this is a customer, potential customer, and then I compare at the end how well they did, because I know the answers.
So at this point, do you abandon one of the algorithms? Do you just say, I'm going to go with this one because it's working better?
Yeah, I mean, then you pick the best algorithm, and then you perhaps want to try this or compare this to another algorithm again at a later point. Because I open sourced the repo for doing this, and pretty soon one guy checked it out and managed to beat my random forest algorithm with another algorithm. So this is a continuous process where you kind of try out new stuff all the time. And if you clean the data differently, other algorithms may come along and beat your chosen one, even though they didn't beat it with how, given the data you cleaned the first time.
So at this point, you have this algorithm, this random forest algorithm that works well enough. You can basically turn it into a back-end piece of software. And then if a sales rep ever has a company that he or she wants to find out, hey, is this a good pre-qualified lead? The sales rep can just, you can make a front end, and the sales rep can just enter in the company name, and then you can have the company name be accessed by some external API. I know there's companies like Clearbit that broadcast things like a company description, so you can easily map a company name to a company description.
Yeah.
That company description can automatically be put through your random forest algorithm, and then the sales rep at the end of that workflow receives the answer, hey, is this a company that you should pursue or not?
Yeah.
So I get that you can now have a binary classifier for brand new companies. You can easily get their description and classify it. Explain how the algorithm is going to learn over time. Does it continue to learn, or has it already learned? I mean, we hear this term machine learning. Does that mean that the algorithm is continually updating, or has it already learned?
So right now, this is only a script, and the algorithm has been exported so that the sales guys can run it on their computers, or they can run the script on their computers. However, we do have plans to improve the algorithm basically by feeding it more data, meaning that after the sales reps has used this classifier, they give me the data back to me, and with like, okay, this was classified, this was misclassified, this was correct, this was not, and then I can feed that data into the algorithm again, so that it'll be a little bit better at each iteration at qualifying companies. And it almost always helps to give the algorithm more data. I mean, you can tune the parameters and try new algorithms and all that stuff, but giving it more data is like at least when you have as little data as we have now, is like a certain recipe for better performance.
Right. So I really like this article. I really like this whole story because it's a very practical example, it's a somewhat simple example of how you can use a simple use of machine learning, a simple script to dramatically improve the workflow. Do you have any perception of how much this has improved the workflow of those sales reps?
So it's not used by all sales reps at the moment because we haven't turned it into a product yet. You have to run the script. So we have to do some kind of UX work before all the sales reps will start using the script. However, when Edward, for example, who's been my partner in this, has built it with me and provided me with a lot of help in terms of understanding the sales process, he uses this when he has big lists of companies. For example, Excel spreadsheets of maybe 1,500 companies. And it would take him days to Google every single company, look at their description, try to roughly guess whether or not it's interesting, and then classify them or do whatever, put them into the sales system or whatever. So just by getting that rough sorting from this script saves him a lot of hours. So I don't have an exact amount of hours we save, but it's when they have big lists, it's a lot.
Right. Okay, so I want to wrap up by talking some about how you got to Xeneta and why you are doing what you're doing there. You were not originally a software developer. You're fairly new to machine learning.
Yep.
Can you describe the process for how you became a developer and why you decided to jump on machine learning after having very little background in programming and just what you're doing with your career?
Yeah, so I studied economics at university, and after university, I ran a small startup creating kids' book apps. I did that for about 2.5 years until the company ended up not succeeding. It basically failed, and the three of us who ran it, had to start finding other things to do. So that was about 1.5 years ago, and at that moment I had been coding as a hobby for a couple of years, just because working with apps and kids apps just made me interested in understanding this coding thing. And so I started getting into it. And once we shut down Propel, which our kids app company was called, I got the opportunity to jump into coding full time. So I went to London to a coding community and boot camp, which is called Founders and Coders, which is it's a free coding boot camp for people who are interested in breaking into the software engineering profession, or people who are already software engineers and just want to hone their skills. So I did that for 4 months, and then came back to Norway and got a job at Xeneta, which I also knew from my times in Propel, because they were part of the same accelerator as Propel for a period.
What's the business model for that boot camp if they're free?
So they're a community-driven and a non-profit, and it works by carefully selecting people who are actually interested in being a part of the Founders and Coders community. Because once you've graduated from Founders and Coders, you're encouraged to either stay around and work as a consultant from the space. And when you do that, you pay a little bit back to the school. And also you're encouraged to help out with the next cohort and basically be a mentor or a teacher. So they don't hire any external teachers. They have a core team of 3 people who run the school, who are developers as well. And then the community helps out whenever there's a new cohort coming in. And they take on some consulting work. And that's actually also a part of the last month in my cohort. We did small MVPs for companies for a little bit of money. Yeah. So it's a brilliant community, which has helped so many people, including myself, learning JavaScript and software engineering in general.
Yeah, it sounds like it. So I'd love to just wrap up by, do you have any words of wisdom for people who are learning to program right now? I think there are a lot of listeners who are in a boot camp or they're somewhat early on in their career, how are you feeling about the transition to a developer from a person who was not a developer?
So it's definitely a long walk. It takes a lot of time, and you should feel excitement for the subject. I mean, for coding and building stuff and engineering. But it's actually getting started and earning a little bit of money by coding I'm not going to say it's not hard, because it's hard, but it's not that hard. I mean, it is definitely possible to do. And if you put in the hours, you can fairly quickly start seeing results, both in terms of products you build and you can make money from it. So in that sense, learning to code is you get a lot back from learning it, as opposed to, for example, learning maths, which is very hard to start using practically and benefiting from early on. So I would say look for opportunities where you can use your craft as early as possible, either for yourself and for others. And don't worry about understanding everything from the beginning off. I like to do things before I understand them. I've written about this in my Medium blog, because I think it's important to get excited about what you're doing and not just read documentation and theory from the beginning off. I mean, just jump into it, create something, and then address the part you don't really understand, which you kind of jumped over.
Yeah, I completely agree with that. I think one perfect example from this discussion is we kind of glossed over what random forest and k-nearest neighbor are, and I'm sure you and I both could delve into those algorithms and understand them in more detail, but I would much rather take the approach of shoot first, ask questions later, because by not looking up what those algorithms do in detail, you shipped the product faster and you accomplished what you needed to faster. You saw the end result of what you needed to do faster. You delivered results for the sales reps faster.
Yeah.
And I think that's what I always say is I think is most important about the process of learning to code is getting the fast feedback loop of making yourself feel good by seeing results, and results are often inversely correlated with understanding some of the finer details of how the code you are writing works. And I know that there are people that vigorously disagree with this philosophy of writing something first and then understanding it later. But, we each have our own.
Yeah. And it's, I would say it's so much easier to then understand it after you actually used it a little bit.
That's right.
And you have the motivation to understand it because you realized how awesome it was to build stuff with it and how the awesome products you can build with it. And I think it's, as you said there, machine learning is a great example on that, because it is a very kind of hot field right now, and something I've spoken to a lot of developers who also show interest into it, but kind of fear it in a way because it sounds so extraordinarily complicated. However, it's not if you attack it from the top and not from the bottoms up. If you go top down,
right? And I like that you just call what you made. It's just a script. You created a script with machine learning, and that's all it is. That's all your end result is just a script. But it's machine learning. You trained an algorithm the algorithm learned to identify companies as pre-qualified sales leads or not, and it really wasn't that complicated. And so with that, Per, I want to thank you for coming on the show. Everybody should check out your blog post. It's a really, really concise explanation for how to train a machine learning model. I think it's one of the best simple explanations for how machine learning is so practical, why it's so practical, why this is a really hot field. So thanks for writing that post, and I look forward to seeing more in the future.
Well, thank you. It's been a pleasure to talk to you.